So a creature is constrained to move in one direction within a tube. A scientist measures the velocity of the creature over time and notes that it closely follows the equation that's given here. V is in millimeters per second and T is in seconds. So where is the creature located in the tube relative to its starting point after 10 seconds? So the first step that we're going to need to take is to go ahead and convert this equation for velocity into one that's able to describe position, because we're looking at where the creature is located over time. Okay, so this is position. So what we need to remember then is that velocity is the rate of change of position over time. So we can write that as a differential as v is equal to, if we call position s, okay, it's going to be ds on dt, okay, the rate that position changes over time. So let's go ahead and substitute that into our equation for velocity. So rather than writing it as v, we're going to write it as ds on dt, and it's equal to this mess on the other side, minus e to the negative t. So now what we want to do is get an equation for s on its own. Okay, so that's going to involve solving the differential equation for the general solution. So I'm going to use the separation technique, which means that we want all the s's on one side and all the t's on the other side. So I can do that by multiplying the dt to the right hand side of the equation. So that means I'm going to get all of this stuff multiplied by dt. And at this point, I've actually achieved separation because all the t's we can see are concentrated here, and the only s is on the other side. So at this point, we're able to integrate both sides of the equation. And remember that we can pop a 1 in here if it helps you out, to integrate 1 with respect to s. So let's do that. The integral of 1 with respect to s is just s itself. And now we need to integrate all of these terms with respect to time. So for this first one, it's just going to be the power rule, where we add 1 to the power and divide by the new power. So remember, there's a little implied 1 in here. So 1 plus 1 is 2, divided by 2. For the next one, I'm going to leave the 4 at the front, and then we need to integrate sine of t with respect to t. So when we integrate sine, it actually goes to negative cos. So we'll pop that in there. And then this last one, we want to integrate it with respect to time. So the integral of e to the negative t is going to be e to the negative t. But then we need to remember that if we take the derivative of this, it should go back to what we started with. And if we take the derivative here, we're going to end up with the negative e to the negative t, but we'd multiply by the negative 1 that falls out of the derivative of what's up the top here as part of the chain rule. So in order to get around that, I need to multiply it by negative 1. Okay, so if we take the derivative of all of this now, it will go back to negative e to the negative t. So I can clean this up a little bit. 2 divided by 2 disappears. Overall, this becomes negative 4 cos of t. And we have a double negative here, which goes to plus. So we get all of that. And I've just realized we did an indefinite integral, so we should have our little plus c on the end, okay, holding the place of the constant. So what we've got here becomes the general solution to the differential equation. General because we've still got a constant in here that we don't quite know. So how we're going to move from the general to the unique solution is we need a condition, okay? And what we're asked to do in a moment is to look at where the creature is located in the tube relative to its starting point after 10 seconds. So we need to figure out, kind of using this starting point, what we can do for a condition. So the easiest thing to do would be to say, okay, initially at time is equal to 0, it's at its starting point, and I'm just going to say that its starting point is equal to 0. That's the easiest thing to do. So we're going to measure it from a position of 0. You could equally pick somewhere else to measure from, but then you'd have, I guess, an additional calculation at the end, which is looking at how far it moved from that other arbitrary starting point. So let's use this as our condition and pop it in here. So our condition is s equals 0 when t equals 0. So we're going to get 0 is equal to 0 squared minus 4 times cos of 0 plus e to the negative 0 plus c. So this disappears to 0. Cos of 0 is actually 1, so we're going to get 4 times 1 in here, and e to the power of 0 is 1 as well. So we've got negative 4 plus 1, which is equal to negative 3. So overall, c is just going to be equal to, swing this to the other side, 3. So that means that we can write out a unique solution to the differential equation, which is just going to be filling in the general one with our newfound constant. So c here on the end becomes 3. So now we should be able to figure out where that creature is located relative to its starting point at any particular time. So up in the question, we're asked to figure out at 10 seconds what's actually happening. So let's find out. So when t is equal to 10 seconds, what is the position equal to? So subbing in 10, it should just be a matter of popping this into the calculator, noting that your calculator should be set into radians mode so that when it does cos of 10, it's assuming 10 is in radians. That's because radians are the natural kind of unit for angles, not degrees. So when you pop all of this in, the answer you come out with is 106.4. The units are going to be millimeters, since earlier we were working in millimeters for velocity. All right, we had millimeters per second. So now we've got our answer of 106.4 millimeters. That's telling us relative to the starting point, since we were measuring from s is equal to 0. So this here is distance from starting point. So that's all there is in terms of this question.